So extreme waves are abnormally large events within the open ocean. The first time these were registered was actually in 1995. And as seen here in the photo on the left, the scale of these events without experiencing them is just somewhat phenomenal. This particular event in 2007 is the same height as 6 double-decker buses stacked on top of one another. Alternatively, that's the size of the largest passenger plane in the world, the Airbus A380, inside it. These waves also have significant momentum. They travel in excess of 70 kilometers an hour. Perhaps it's inevitable that existing offshore installations have experienced the price of an inadequate knowledge regarding extreme waves, such as a failed structure in the Gulf of Mexico. But we're entering new frontiers in offshore installations, particularly in the world of structural mechanics, where we are putting energy infrastructure in deeper, more remote, and more hostile waters. With this requirement comes the necessity to better understand extreme wave loading and extreme wave processes. So this is a two-stage process. You might have noticed mankind has a habit of placing structures on the surface of the sea, ships, oil and gas installations, and also offshore wind turbines. But this is problematic because it's at the sea surface where the waves are largest, where the velocities are largest, and this causes the largest loads. So how do we design to better survive for these forces? So this is a two-stage process, the first of which is to better understand the actual incident wave conditions itself. The second of which is then to better model the improved fluid structure interaction. To show the benefit of this work, one particular element of this loading process is discussed. That's impact loading. We potentially all know this from observations at the swimming pool, that awkward moment when you see someone diving and it goes wrong and they land belly first. That initial force that you have is what is very important in structural design, and particularly offshore structural design, because it's where the largest loads occur. So that's what we have to better design for. And this is the problem, epistemic uncertainty. So with impact loading, epistemic uncertainty is high. So this means that when we predict the force, or we use a loading model, there's a lot of uncertainty not due to natural variability, but we're due to poor physics within the model. And that's what my work looks at reducing, is this uncertainty. So by example, if we use current design norms, we see there's a large range in typical loading coefficients that are used. So they range from 2 to 14. So that means we have a huge spread in our load predictions. If, however, we can improve this physical model, i.e. reduce the epistemic uncertainty, we can reduce the variability of this load, and this is shown here, down to 2 to 3.5. So if we can reduce this load, that is a huge benefit. Reducing these coefficients is really important, because it means ultimately you can better predict the forces that your structures will be subjected to, and ultimately you can predict when failure might happen before it actually happens, like in the first picture. Thanks very much for listening.